Okay, so today's topic is actually embedded systems, what kind of digital signal processing things you need to know when you are designing the software for embedded systems. Kind of fits nicely into the as a capstone kind of thing. Let's see. I have some brief notes again, but mostly again this is more about doing it in practice or practice it by doing. And basically some considerations. First of all, everything when you are doing on embedded system is about performance. The less performance you need, cheaper the devices. So if you can do all sorts of stuff if you have unlimited resources. Okay, so all of these filters, what we have been doing, the floating point calculations, if you have enough of resources, just like, for example, in this mobile phone, there's enough of resources to do even video streaming and stuff like that, playing games on mobile phones. Okay, but if you are, and you always are, you're electronics engineers, so you will be working on embedded systems at some point. And then you will find out that, okay, if you're making small scale production or design for small scale production, small means less than 1 million. When you have to buy the components yourself from the shop and you don't have enough of volume to make actually mass products like several tens of million pieces of processors and such kind of thing, then you basically just need to take a look what is the lowest performance processor needed for doing that stuff. And digital filtering requires arithmetic operations like add and multiply. And actually that's all you need. So for example, a second order system basically is the one that you have the difference equation, something like that. This b0 xn plus b1 xn minus 1 plus b2 xn minus 2, and then we have minus a1 y n minus 1 and another feedback term a2 y n minus 2. So this is a fundamental second order system block, what it does, the difference equation. And it has 1, 2, 3, 4 additions and 5 multiplications. Actually, it has 6 multiplications because, well, usually there's also a common the multiplier for all of this. I call it just C. Okay, so lots of multiplications and some additions. So that's basically why we have kind of nice the operation called multiply accumulate operation, which is the basic unit for any digital signal processor. And for example, that makes easy to calculate the direct finite impulse response calculation. Or, well, this is also easy on this multiply accumulate if you have that kind of command. Most of the command these modern processors do have multiply accumulate the command. If it's say even some 8 bits, but that's weird. Okay, but anyways, for example, ARM processors do have, and they actually do also have some cores have even the digital signal processing special instruction sets, meaning that there's hardware to do this multiply accumulate operation fast. Okay, but anyways, there's some code how to do this multiply accumulate in real life. Okay, accumulate, meaning that we are adding to the previous value, and then what we are adding, well, the x, the input values, weighted input values, basically. They're weighted by the filter coefficients or impulse response. Okay, good. That's just an example of how to do the calculations. If you have a special ARM processor, for example, which does this one, then you need to go and apply that function. But fortunately, for example, in the case of ARM, the processor manufacturers actually are giving those for free. The code, subroutines are already there. You just start using them. So those are usually optimized routines for good reason, to get the best performance. Okay, so that is needed. So basically the floating point implementation would be easy, but fixed point usually gives you better performance. It's just plain, well, electronics. How many gates you need to make the hardware floating point processing unit compared to fixed point. Floating point meaning 40 bits operations with the exponent and mantissa. So think of the complexity of that structure when you do it on FPGA. And yes, this can be also done in FPGA. And actually the fastest digital signal processing systems usually employ FPGA because you get parallel processing. Not easy, but can be done. Okay, so yeah, modern processors usually have a MAC unit. And yes, this is like an IKEA store. Some assembly is required. Yeah. Hardware, software, floating point arithmetics. Okay, what does it say? So yes. If you run this floating point arithmetics in, for example, 8-bit processor, I do not recommend it, since it takes actually thousands of instruction cycles to do a simple multiplication or addition. Okay, then there's also multiply add acceleration in some processor sets. Take a look at, when you have decided what processor the architecture you're using, take a look at the manuals or selection sheets. If there is a MAC unit, it's always mentioned if there is a MAC unit. If you have a digital signal processor or any other that requires, well, multiply, accumulate operations, if the system is going to do some calculus, you save a lot of energy by taking a processor with a some hardware multiply add acceleration on the processor. Okay, then there's this special processor families which are called like digital signal processors. They are designed for doing the fast multiply accumulate. And if the system is, for example, a digital filter for this network data or radar or such, then basically this is still current technology to do it. They are also pretty good on automotive applications where you have, say, several sensor data coming and you need to do fast calculations, for example, for deploying the airbag or some other time critical stuff. Okay. Most of the cases you're working with the fixed point arithmetics, meaning integers. practically it's a signed integer. Small embedded processors cannot actually do those so fast. So it means that we just have to fix the filter for so quantize the filter, meaning that we are taking the nearest fixed point value between minus 0.999 to plus 0.999. So plus minus 1 and those highest and lowest not included. So that's basically the fixed point value. And you can actually calculate those values using this normal integer arithmetics. But anyways, so that's a real life example what can happen for IIR filter when you start quantizing the parameters, meaning the lowering the computing calculation accuracy. Okay. And there's also note that in a bad case, quantization of the IIR filter coefficients can actually move the poles outside of the unit circle. Think of for example, that notch filter. And make it really, really, narrow bandwidth notch filter. First of all, this angle here. If you have quantization of these coefficients, it means that not all the big points can be achieved. So basically, this 0 probably moves somewhere due to the quantization, meaning that this does not anymore have exactly the required stop band attenuation. Also, the angle changes. Okay. And then basically what can happen if you have enough of the quantization, your pole can easily jump outside of this unit circle. That's a bad thing. Yeah, it's unstable, so it means that it's unusable. In any case, you need luck to keep the 0 and pole actually on the same complex angle. So fundamentally what will happen, you will get usually something like that. Well, not even like that. Maybe something like that as your notch, the amplitude response. So not anymore infinite attenuation and then skewed the amplitude response because the notch and the 0 and pole are not on the same angle. You get amplification on different side or either side of this attenuation angle. Okay. How to avoid or reduce the risk? So basically what we can do is to go into second order systems. Why this one would help? Well, first of all, second order systems. You can divide any system as second order system. Think of for example, something like that. So we have this notch and then we have zeros and poles. Wherever they are, you can always arrange these so that you take, for example, these as one second order system, these as another second order system, then we have this notch as the third second order system. So it's easy to make those different systems, put them on cascade, meaning you're multiplying the transfer functions like this. So yeah, SOS1, SOS2, SOS3, and that does the whole trick. So how this one actually helps. Think of a simplest possible system, which is the no, that's not the simplest. Well, yes, simplest possible low-pass filter system, which means that you put enough of zeros here, nth order system which has n zeros on the highest frequency, Nyquist frequency, and then you have n poles here, meaning that you have basically system which is x n minus 1 minus plus 1. Okay. No, sorry. xn plus 1 x n minus 1 plus 1. Oops. And so on. So basically, this is the product of x n minus k plus 1. How does it go? Am I okay here? Maybe. K from 1 to n, something like that. Well, who cares? You do. Okay. Then it actually starts from xn minus 1. Starting to xn. Okay. Anyways, that's the corresponding the y of n directly from z, which basically is either, well, those multiplied, meaning that it does x of n plus, well, think of the x n minus 1 plus second order would be like this. This is for the second order. Third order would be 1, 3, 3, 1. Next one, 1, 4, 6, 4, 1. That comes from the triangle of the powers. Remember x plus 1 to the power of n, that triangle from the high school. Right. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, something 4, 1, 6 or 9, I don't remember. 6, no, 9. Is it the... Okay. 6. This is 6, yes. Higher the order number is, for example, 100. It's around 100. If you have a direct form system, you have decades of difference between the biggest number and smallest number that you are trying to make the weighted average. So basically, these small numbers will round to 0 if you keep that one, or you will actually overload the system. It's either the arithmetic overflow, or some of these values will go to 0. If you are keeping this one as second order system, you are always calculating with the numbers which are relatively same, on the same order of magnitude. So basically, this breaking up a system in the second order system will help you on keeping the this system, say, accurate. So it's minimizing the quantization error. Okay. In that picture, I have an example of a system I think it's the same as the previous one. The floating point arithmetic is the blue one, which is more or less as the 8-bit second order system of the amplitude response. If you take the 8 bits direct form, meaning you calculate it straight from the difference equation, then the performance is like this. So you are starting to lose the stop band attenuation because of that one, and then okay, it usually also gives more trouble also on that passband. Okay, another example, 6th order elliptic, and so basically that's the big. I see now. So this one was a finite impulse response system, and quite typically you are starting to get bad values, especially on this stop band. But on the case of IIR, you're getting problems on the passband. Well, passband is actually defined by the poles, the location of poles, more or less, in IIR systems. So small change in this distance will make a big difference on amplitude response. Quite the same as in the case of FIR, the step and attenuation depends on these zeros on the unit circle. If they are not on the unit circle anymore, then you start to affect on the stop and attenuation. Okay, so that is the brief introduction to the this topic. Next we go and try to do something on with the MATLAB. Let me first do something here.